In the last video, we put together an iterative solution for the Fibonacci problem. We're now going to continue by putting together an alternative solution that solves this by using recursion instead. Now, of course, as usual, we will make a backup of our iterative solution here. So I'm going to copy our previous effort. I'm going to move down to the bottom of the file and paste it, and then comment that thing out. I'll then go back up to the original implementation up top and delete the contents of the function. Okay, there we go. Now, before we put together this recursive solution, I want to tell you kind of a funny story that I think is great commentary on the state of coding interviews in general. And this is something that we've been discussing all through the course. So I have worked at a company in the past, years ago, where every interviewee that came in, every engineer who was interviewed, they would all come in and we would always ask them the same problem. We would ask them, hey, solve Fibonacci using recursion. And I got to tell you, there was two types of engineers. There was two types. There was one type who could solve it. They did a great job. They solved it using recursion. And then the other type, the other engineer, they could not do it for the life of them. And you might be curious what the difference between those two engineers was. And this is from my own practical experience. I'm very much convinced of this. So what was the difference between the engineers who could solve it and couldn't solve it? Well, at the end of the day, there was one simple difference. The people who could solve Fibonacci using recursion had already seen the problem before. That's it. So this is the classic problem where if you see it one time, you say, oh, okay, yeah, that looks reasonable. I can memorize that. And then you say, okay, that's how I solve Fibonacci using recursion, because it is a classic example of recursion. However, if you've never seen it before, it's so incredibly unlikely that you will come up with this solution to Fibonacci using recursion that I'm about to show you. It's, in my opinion, it's just really challenging, extremely unlikely. I'm sure there are people out there who have came up with this solution independently, but I am very much convinced that this is an example of a problem where you've either seen it or you haven't. So I'm very happy you're here watching this lecture because it means that you will see this solution and you will be able to answer this question when it comes up in your own interview. By the way, Fibonacci series is an incredibly common question to be asked, so this is definitely one to keep in your head. All right, so let's do this. Because of what I told you, this is a problem where you've either seen it or you haven't. I'm just going to put the code up here for the solution, and then we'll talk about the solution and how it works. Like I said, it's really challenging to come to this solution on your own. My personal opinion, of course. So we're going to say if n is less than 2, return n. And then otherwise, we want to return fib n minus 1 plus fib n minus 2. And that's it. That's the solution right there. So let's flip on over to our terminal. I'm going to save this file. I'll flip on over to the terminal and I'll just verify, yep, it looks like our tests are still passing here. So very good. Well, kind of very good. So why does this work? There's a couple different things I want to talk about with this Fibonacci solution right here. The first thing I want to do is tackle it from kind of the recursion side and understand how the recursion here works. After that, I want to come back to the solution and talk about the differences between this one and the one we worked on before from a time complexity standpoint. So understanding this recursive solution right here is really challenging unless you put it into diagram format, which I've done. So let's go take a look at that diagram. Now, before we do, one thing I want to point out here is the only time in which we appear to actually return a number from Fibonacci right here is when n is less than 2. So when n is equal to 0 or 1, that's the only time that we're going to return an actual discrete number. So with that in mind, this is one thing I want you to be aware of right here. When we call Fibonacci with 0, we get back 0. When we call Fibonacci with 1, we get back 1. Those are like very discrete numbers that we definitely get. Every other call to Fibonacci, like if we call Fibonacci with 10 or 5 or 6, well, it means that we start entering into this recursion, and that's when we start having to think about, okay, how do all these function calls stack up and eventually give me a result? So with that in mind, let's take a look at a diagram that's going to help us kind of understand what's going on here. All right, so at the very top, we have an imaginary function call to Fibonacci with an input of 5. So as you just saw, let's take 5 right here, and let's go back to our code and think about what would happen. So we called fib with 5. Is 5 less than 2? Well, no, of course it's not. So we call Fibonacci with 4, and Fibonacci with 3. So that results in 2 function calls. And that's what I'm reflecting this diagram over here. Here's Fibonacci being called with 4. Here's Fibonacci being called with 3. Now in the case of 4, let's walk through the case of 4. So fib of 4, or n equal to 4, is 4 less than 2? Well, again, no, it's not. So we call Fibonacci with 3 and Fibonacci with 2. And then the process repeats itself for the rest of this tree right here. So eventually we get down to the bottom of the tree, and eventually we hit that case where n is less than 2, and we start to actually return some numbers. So that is these blue squares right here, all these blue squares. This is where we actually return some numbers. Now, as you saw just a second ago, right here, so whenever we call Fibonacci recursively, we are adding the result of those two together. So at the end of the day, you can kind of imagine that all these blue squares right here are eventually going to be added up and totaled together. So let's take all these different blue squares right here and take their sum. So specifically, what calling Fibonacci with this particular number would result in. So when we call Fibonacci with 1, it returns 1. If we call Fibonacci with 0, it returns 0. So we don't really care about Fibonacci with 0 because it returns 0. So I'm going to just kind of like gray those out. All we really care about here is calling Fibonacci with 1. So when we call fib with 5, it eventually results in Fibonacci being called with 1, 2, 3, 4, 5 times. So we can add together 1, 2, 3, 4, 5. Okay, so Fibonacci of 5 should be 5. Let's go back to our diagram right here, or the sequence right here. So element 0, 1, 2, 3, 4, 5. So 5 is 5. That is definitely the correct answer. So that's how it works. Basically, we keep on calling Fibonacci with smaller and smaller numbers until eventually we meet this base case right here and start to return some actual value. Now, that's kind of easy to think of for the fib 5 case. Let's look at just one more case here when we call Fibonacci with an input of 6. So here's what the diagram looks like with 6. And yes, this took me a couple minutes to make this diagram right here, but whatever. So we call Fibonacci with 6. That, of course, results in a call to Fibonacci with 5 and 4. And then we go down this tree, and eventually we collect all these 1 terms and add them all together. So we get 1, 2, 3, 4, 5, 6, 7, 8. 8 is our total. Let's go look at our series again. We get 0, 1, 2, 3, 4, 5, 6. So calling Fibonacci with 6 should return the 6th element in the series, which is 8, and that's exactly what we got from this result of adding these all together over here. So that's how the recursive solution works. Does that sound confusing? Well, it very much should. Gee whiz, I really think that it should. I can't imagine why an interviewer would ask this thinking that someone's just going to bust out Fibonacci on the fly with this recursive solution right here. Honestly, a lot of interview questions, especially coding questions, are not so much designed to test your ability to generate solutions. They're more testing just to say, hey, do you have the common knowledge that we expect someone interviewing with our company to have? In other words, I'm kind of convinced that people are asked Fibonacci here just to make sure that you know or you have seen the problem Fibonacci before. Because if you haven't seen it, maybe that's some commentary about your experience in the computer science field or something, I don't know. That's the only reason I can personally really imagine that Fibonacci is asked in a recursive type of context. Anyways, enough of my ranting here. Obviously this is a question that gets me a little bit upset. I have been asked this question in an interview, and you know what? I did pass it solely because I memorized the solution, not because I understood at all how the recursion was working. And so I guess that's why I get frustrated at the question, because it really proves nothing about your interviewee. Okay, anyways, enough of that. So I do want to have a good discussion about time complexity for this recursive solution right here, because it's actually quite awful, and you might be surprised to see how bad it is. So this whole time complexity discussion around Fibonacci, I think perhaps that's why interviewers ask this question, because it is a great problem to kind of profile your understanding of algorithm performance and time complexity and all that kind of good stuff. So let's continue the next video. We're going to do a kind of deep dive on time complexity between these two solutions, and we'll talk about some possible solutions to improve the time complexity of a otherwise very slow algorithm. So quick break, and I'll see you in the next video.